Hello. So in this video, we're going to be looking through Haberman's section 2.5, which in practice is just more examples of separation of variables and the resulting series solutions that you can construct. Okay. But maybe a little more broader scope, we're going to be talking more about Laplace's equation, what it looks like for kind of different geometries. And then we're also going to talk about some qualitative properties that solutions to Laplace's equation have. And so what is Laplace's equation? So here we're asking for a solution Laplace squared u is equal to 0, which usually, right, so this usually arises as an equilibrium solution of the heat equation, right, where equilibrium, right, time derivative of your temperature is 0. Okay, so usually, right, this is how it arises. And so in general, what we'll do is we'll say, well, in higher dimensions, okay, we can write out Laplacian in certain ways. And so then what we're going to do is we're going to apply separation of variables to kind of, right, Laplace's equation, move things around, solve things, etc. But yeah, so it'll just give us more practice with separation of variables and constructing a series solutions. Okay, so in practice, what are we going to do? Well, we're there are three main pieces, right? So first, we're going to look at what Laplace's equation looks like on a rectangle. Next up, we're going to write same equation, just we're going to change the geometry. So instead of a rectangle, now we're looking at a disk. And then finally, we're going to talk about a few what I'm calling qualitative properties. But they're going to give us some intuition about, in particular, how solutions depend on kind of this boundary information that you prescribe. And so we'll see what that really means in a minute. Okay, so Laplace's equation in a rectangle. So in 2 dimensions, right, what does a heat equation look like? Well, the time derivative is equal to some constant times Laplace squared of u. Okay. So the question is, what does this thing look like in 2 dimensions? Well, this thing looks like this. Okay. And so if we want an equilibrium solution, we're requiring that the time derivative is 0. Okay. So plug this thing in right there, you're left with this after dividing by k, but right, you have a 0 on one side, so it doesn't matter. Okay, so this is Laplace's equation. This is the thing that we're going to be looking at now. Okay, and so kind of to state the problem a little more quantitatively, what we're really interested in doing is saying, right, we have some rectangle, okay? In coordinates, how are we describing the rectangle? We're describing it like this. Okay, we want to find an equilibrium temperature solution, which means we want to solve this. Okay. Right, but we also need to specify something about what's happening on the boundary. Okay, and so in this case, we're going to have 4 boundary conditions, right? Because there are 4 edges of our rectangle. And so then the question is, well, what does this setup look like? So let's draw a rectangle, something like that. Down here, x equals 0, all the way up to x equals L, right? Because the x coordinates go from 0 to L. Likewise, over here, we have y equals 0, all the way up to y equals h. I guess that's what's written right there. Okay. And so now the question is, right, what do these boundary conditions look like? Okay. Well, for example, we're told at x equals 0, okay, the value of our temperature, so at x equals 0, so along this line, the value of our temperature is going to be this function g1, okay? And so maybe g1 looks like that. And so the picture to keep in mind is that this sketch of g1 is like a curtain right above that boundary piece. Okay, so that's one of them. So this is g1. We also have information at x equals L as a function of y. So we might draw that as something like that. And so again, this is a curtain. Maybe if it dips below, then the curtain's below that plane. Okay, but then this might be G2. Okay, likewise, at y equals 0, u is going to be this function f1. So, right, take the line y equals 0, which is that. Maybe we're going to draw something like that. So this is the function f1. And then finally, up top, we have our function f2. Maybe I should have drawn it as continuous, but it doesn't matter. Actually, yeah, I'll draw continuous. And so then this boundary information up here is f2. Okay. So what we're asking for is, right, we want to find a function u so that on the boundary, u looks like any of these functions, okay? But then on the interior, we want this function u to satisfy this equation. Okay. And so what we're going to do next is we're going to essentially give a way to compute what this function looks like explicitly in terms of kind of a series solution in sine for one of the variables. Okay, but in practice, it means we're using separation of variables here as well. Okay, great. So one observation is, well, sure, when we have, all four boundary pieces of boundary information, okay, like all of this stuff, probably pretty hard to solve. And so what we're going to do is instead, we're going to solve the slightly simpler problem where we say, well, only one of the sides is boundary information. All of the other sides, that boundary information is 0. Okay. And so what that looks like is now we're interested in solving this problem. Okay. And so then the observation is, well, right, if we know how to solve a problem like this, okay, what we can do is then solve if u of 0, y, if this boundary information was 0, but then here the boundary information was g2 of y, and then everything else was 0. Okay. So solve this problem with 0, non-zero, 0, 0. Solve the problem with 0, 0, non-zero, 0. And then finally 0, 0, 0, non-zero. Okay. Because then what we can do is, right, those four solutions, we can add them together. And so, right, on the interior, since we have a homogeneous or linear homogeneous equation, adding these four solutions together, right, each of those four solutions satisfies Nabla squared u is equal to 0. So their sum is also going to solve Nabla squared of the sum is equal to 0. likewise, or yeah, and then when we look at the boundary information, right? So if U solves this, and then maybe our other solution, maybe U prime solves this, actually, so let me write it out. So then, so U1 solves, right, U of 0y is equal to G1, U of Ly is equal to U of x0 is equal to U of xh, 0. And then U2 solves U2 of Ly is equal to G2, and these are functions of y. And then U of 0y is equal to U of x0 is equal to U of xh. This is all 0. Then U1 plus U2, the sum will solve this equation with the boundary conditions. U of 0y is equal to G1 of y, right? Because U2, right? The behavior of U2 at 0, U of 0 comma y, that's just 0. So when you add these together and then you restrict to x equals 0, you're only going to see the contribution from U sub 1. Okay. And then, like same argument, right? If you restrict to x equals L, you're going to see a contribution from U2, but no contribution from U1. And so you're going to get U of L comma y is equal to G2 of y. But then you're 0 on the other boundary components. And so then you're going to have U of x0 is equal to U of xh, which is 0. Okay, so the point is, right, we can solve 4 individual problems where all of the boundary conditions here are 0 except for one of them, sum them up, then we're going to end up with something that works for kind of, right, the full problem. Okay. But here what we're going to do is just for, you know, ease of computation, we're going to restrict ourselves to this problem where we're looking for a function u that satisfies this, such that u takes that value there, and then it's 0 there. Okay. And so as mentioned, right, we're going to look for product solutions, okay, separation of variables. So we want solutions of this form. Question is, well, what do the boundary conditions become? So in this case, right, keep in mind, so the boundary conditions here, and let me copy this. Oh. Right, so these were the original boundary conditions. So this becomes, right, h of L phi of y is equal to 0. And then this is true for every possible y. So then this implies that h of L is 0. Likewise, for example, this one gives us that h of x phi of h is equal to 0. And this is true for every x. So if we want a non-trivial h function, then this should give us that phi of h is equal to 0, etc. Okay, so if we want a product solution for this PDE, then these are boundary conditions coming from kind of what we originally had. Okay, and so keep in mind that here, right, this one doesn't really tell us much about kind of h of 0 yet, right? Because if you plug in the product solution, this one becomes h of 0 of, or h of 0 times phi of y is some given function g1 of y, okay? And then, of course, here, phi is our unknown function, okay? And so, yeah, doesn't really give us anything about h, okay? But later on, we'll come back and we'll revisit this condition once we've constructed our solution. Okay. Okay, so now let's use separation of variables. Let's plug these things in, see what we get out. Okay, so if we plug this into the PDE, right, this is what we get. Okay, so what we're going to do, move this to one side, divide by h of x, divide by phi of y. We end up with this. Okay, and so the observation is here, well, okay, so this piece right here is what we get from separation of variables. And the observation is, well, the left-hand side only depends on x, the right-hand side only depends on y. So each side is a constant with respect to the other. Okay, so each side is equal to a constant. And for us, we're going to call that constant lambda. Okay, and we're going to keep a positive sign with this constant because we have a negative sign right here for reasons that we'll see in a second. Okay, but this is what we get from separation of variables. This is all equal to a constant. Okay. Okay, so rearranging things, right, you're going to end up with two ODEs, these two pieces. Okay, when we were working with the heat equation, this looked like dg dt is equal to kind of lambda kt, or lambda kg, right? Something like that. A minus lambda kg. Okay, but here, right, because we're working with Laplace's equation instead of the heat equation, right, we have something interesting going on with, I mean, we have, right, two derivatives already. Okay. Okay, anyways. But what we notice is, well, the ODE that we get for phi, okay, by choosing our signs in the way that we did, right? So, yeah, this is the piece that we end up with. And then also for this piece, we have these two boundary conditions, okay? And so this is the same eigenvalue problem from right, 1D heat equation with zero temperature boundaries. Okay, so because we've chosen our signs in the right way, right, half of our problem is already solved. Okay. Cool. So what that tells us is we're going to be able to figure out what this lambda is pretty quickly. We can plug this lambda back in here, use this boundary condition to fix one of the constants here, and then go from there. Okay. Right, so as I said, right, we've already solved this eigenvalue problem. Technically, we need, with the boundary conditions, phi of 0 is equal to phi of h, which is 0. We know that the solutions look like this. Okay. Okay. And so now what we can do, right, is we say, well, we know what lambda is. So take this lambda, plug it into the other ODE. The ODE for h is now this. Okay. And so, right, what do solutions for this look like? Well, in general, right, we're solving this constant coefficient ODE, where the coefficient here is positive. So we know that solutions must look like this. And when in doubt, you can just, go through the process, right? You say r squared minus n pi over h squared is equal to 0 for the characteristic equation. This tells us that r is equal to plus or minus n pi over h. So h is going to be c1 e to the r x plus c2 e to the minus rx, coming from that. Okay. But anyways, right, so this ODE has a general solution that looks like that. Okay, but and so here's, I'm hesitant to call it tricky, but it's a place where we have a lot of freedom for what form of the solution we pick, and depending on the form of the solution, expressions are going to be easier to work with. Okay, so technically, yes, this is a solution, but if we kind of reorganize the pieces, one equivalent way of writing this is this, right? And of course, right, so here it's just a matter of changing what these coefficients look like to get the two to match up. Okay, but this is one equivalent way of writing the solution. And the nice thing about writing in this way is, right, well, these two functions kind of already have names kind of coming from the ODE literature. Okay, and so in particular, this thing right here is what we call cosh. This thing right here is what we call sinh. Okay, and so, right, sinh of x, this is a function e to the x minus e to the minus x over 2. Cosh is e to the x plus e to the minus x over 2. And so, I mean, really, right, they're just exponentials. But the nice thing about writing them in this way is that we get the formulas cosh. Let me start. So sinh prime of x, this is cosh. Okay, similar to with the trig identity or trig functions. And then the derivative of cosh is now going to be sinh instead of minus sinh. Okay, but the point of all of this is, right, solutions to this we can either write as this or as this. And there's one other way of writing these solutions that we'll see in a minute. But okay. Great, so we have our solution, this or this, and then the question is, right, what are these coefficients given that one piece of boundary information we have for this ODE? Okay. Right, so recall the boundary condition for H was that it was 0. Okay. And so what we can do is say, well, we know what the solution looks like, and we have this boundary information, so let's plug the boundary information in, see what pops out. So, right, H of L is equal to 0, so this thing right here is H of L, which is 0. This thing right here is H of L, where we're plugging in L in there. Okay. And so then what we can do here is bring this term to the other side, right? So we can write it out, right? So this becomes minus C2 sinh of n pi over HL is equal to C1 cosh of n pi over HL. Divide by sinh. Actually, I take that back. Divide by cosh. Okay. We're going to get minus C2 sinh of n pi over HL over cosh of n pi over HL is equal to C1. And so then this thing, right, because it's a ratio of, right, hyperbolic sine and hyperbolic cosine, this thing right here is what we're calling tang. Okay, but using this boundary condition, right, we have a relation between the coefficients. So our solution h of x, we can write in this way, right, where we have this unknown constant, okay, but when we use superposition, we're going to have these, right, unknown constants anyway, so we just want one unknown constant. Otherwise, right, what does h look like? Well, it's this linear combination of, right, this constant times cosh of x plus sinh of x. Okay. So not necessarily like the nicest thing or the, you know, it's not necessarily the cleanest expression, but it's an expression, it's a solution. Okay. Great. So what we're going to do is actually not use that expression, but we're going to use something slightly different. And so another choice, another way of writing kind of this general solution H is actually in this way, where kind of the basis that we're choosing is that we're shifting cosh and sinh kind of, we're shifting them over kind of the line and translating them by kind of L units. Okay. And so, right, question is, well, is this equivalent to some of the other expressions? Can we figure out what C1 and C2 are to match it up with whatever? And the answer is yes, which, I don't know, homework. But the nice thing about using this expression, right, is now that things are in terms of, right, where they are relative to L, okay? And so in particular, right, the boundary information h of L is equal to 0. Well, plug in L here and here, you're going to get, right, so h of L is C1 cosh of 0 plus C2 sinh of 0, right, cosh of 0, this was e to the 0 plus e to the minus 0 over 2, which is 2 over 2, which is 1, whereas sinh of 0, this was e to the 0 minus e to the minus 0 over 2, which is 0. Okay, so choosing this representation, right, we get that h of L, that's going to become, so C1, just C1, but then C1 is equal to 0, because, right, that's what h of L is equal to. So in this expression, we don't see this function at all. We just see a sinh of n pi over h, x minus L. Okay. So this is another way of writing what that solution for h looks like. Okay, so this is one option. This is another option for reasons of convenience, and we don't want to write out this whole thing every time. We're going to use this as our product solution going forward. Okay, great. So, right, what we've done is we said, well, right, in solving this problem, separation of variables, what do the spatial pieces look like? They look like this, and we get one of these for each n. What do the, so what do the h dependent pieces look like? They look like this, and we get one for each n. What do the corresponding x pieces look like? They look like this, and we get one for each n. Okay. So when we construct our product solutions, right, because we have constants associated with these, we look at the kind of product solution for the nth functions. product solution, right, phi of n times h of n is going to be some constant times sine in y times sinh in x. Okay. So using the principle of superposition, right, because these all satisfy kind of that PDE on the inside, we get that this is our most general solution. Okay. So now the question is, right, how do we figure out what the a sub n are? And so keep in mind, right, until now, we have not used any information about, right, the value of our function at x equals 0, which was kind of that only, right, boundary information that was non-zero that we were given. Okay. So to get these constants, right, well, now let's match to kind of that boundary information. Or another way of thinking of this is, right, kind of, you can think of it as like the initial condition in x. Okay, but that's what we're going to use now. And so technically, there's a typo. This should read, oh, this is a function of y. Okay. Right, so yeah, what I was saying on the last slide, for this to actually work for the problem that we want, question is, what are these coefficients? Well, if we plug in our boundary information, right, our boundary information is saying what happens at x equals 0. We know that's this given function. So if we plug in x equals 0 here, right, well, what do we get? X equals 0 doesn't affect this, doesn't affect the constant, but it affects this. Okay. And so now this is a constant, this is a constant. So, right, what we have is a sum from n equals 1 up to infinity of a sub n sinh n pi over h minus L times sine of n pi over h y. And so now we have, right, some mystery constant times a sine term, which is exactly the same kind of series that we worked with previously, right? And so we know how to get these coefficients from those series, okay? And so that's what we'll do right now, right? So this is the expression we want. Question is, how do we get the coefficients? Well, right, this is a series in sine. So let's use the same trick we use to essentially kind of isolate, right, these coefficients by integrating out certain sign products. Okay, so from this, multiply by sine of m pi over hy on both sides and distribute this term across the sum. We're going to end up with this. Okay. Now what we're going to do is we're going to integrate from 0 to h. Right? And the reason we're going from 0 to h instead of 0 to L is, well, the functions that we care about, these sine functions, these have period, or I guess half period, but whatever. These are defined from 0 to h, okay? And so because these are the things that kind of we want the coefficients for, the bounds of integration are going to come from that. So yeah, so we're going to integrate from 0 to h. This side can't do much with, because sure, G1 is given to us, but we don't have it in a computable form. Over on this side, what we've done is distribute this integral over this addition, which we're going to say is fine to do. A sub n and sine or sinh of n pi over h minus L. These are constants with respect to y. So when we integrate with respect to y, we can pull these constants right out of the integral. Okay. So we're left with this. Okay. But these integrals right here, right, these you should recognize, right? So these integrals are 0 if n and m are different. Otherwise, they're equal to h over 2 if n is equal to m. Right. So as we look over the sum, right, start with n equals 1. Is it equal to m? Yes or no? Then it'll either be the integral will be 0 or h over 2, right? Keep going. Only one of these terms is going to be non-zero because only one of these integrals is going to be non-zero. And the integral for which this is non-zero occurs when n is equal to m. Okay. And in that case, this integral is h over 2. So this whole thing, the only term that survives is when n is equal to m, and then this becomes h over 2. So we're left with this expression. Right, so on the left-hand side, integral of sine of m pi over h times y times g sub 1 of y. That integral is equal to this mystery constant a sub m times this known constant sinh of m pi over h of minus L times this known constant of h over 2. Okay, so this bring down here, and we've solved for these coefficients a sub m. Okay. So, right, in summary, what have we done? We said, well, if we consider this problem, right, where we have one non-zero boundary condition, all the other boundary conditions were 0. Using separation of variables, we're able to construct a general solution that looks like this, right, where it looks like sine in terms of y, and then this hyperbolic sine or sinh in terms of x. And then the question is, well, what are these coefficients? Well, we can compute them using the same technique as before. And when we use that same technique to compute these coefficients, what we end up with is this, right? So in the heat equation, what these coefficients looked like was, well, we didn't have the sinh term down here. We just had a 2 over h times that integral, right? But now, because this is a little more interesting, I mean, it'll show up, okay? But yeah, this problem, what is the solution? This with these coefficients. Okay, cool. Great, so that's one kind of application of, right, separation of variables, where it's not kind of a time and space problem, it's a space and space problem, but technique is still valid, still works to construct solutions. What we'll do next is change the geometry, okay? And so, yeah, so now what we're going to look at is Laplace's equation, but now in kind of a disk. Okay, and so in particular, what this is going to do is, right, we're going to, since we're changing the geometry, maybe working in polar coordinates is going to be kind of easier and more helpful. Okay, and so what that means is that the form of Laplace's equation is going to look different. Let's see what that looks like. So, right, we're still solving, right, Laplace's equation. If we want an equilibrium temperature, we're still solving du dt is equal to k Nabla squared u. It's just if we work in polar coordinates, okay, Nabla squared u is going to look different. What does it look like? Well, Nabla squared u in this case looks like this. Okay. So this is now the problem that we want to solve. Question is, what are the boundary conditions, right? Well, so let's draw a disk. Okay. Let's see. And so then that's the origin, radius A. And so what we're told is, well, what is the value of our temperature at radius A? Okay. Well, in this case, it's going to be a function of theta, but maybe it looks something like that. Okay. And so again, think of this as a curtain over kind of that boundary circle. Okay, and so we're told this is the initial heat distribution, right, over the boundary of this disk. And then our question is, on the interior of the disk, what is that temperature distribution? Okay. And so we're modeling that by saying, well, on the interior of the disk, our temperature should satisfy this equation. Okay. Okay, so one thing to note, well, in this case, right, as we've drawn it here, doesn't look like a rectangle. But if we write out the coordinates in this way, then we see a rectangle, right? So the rectangle would look like, so r equals 0 up to r equals a. And then here, theta is equal to minus pi. And then up here, theta is equal to pi. Okay. And so, right, our observation from before was that, well, if we have, right, a rectangle, we'd expect 4 boundary conditions. Okay. And so in this problem, we've only really drawn 1. And so then this boundary condition here, this corresponds to, right, at r equals a, we're given some function information. And so then the function might look like, I mean, it's not exactly the same, but it's what's drawn here is just a function over the values of the function over that line. Okay. So as drawn, right, we've only given one piece of boundary information. Then the question is, right, what are the other pieces of boundary information? Well, pieces of boundary information we're going to use are the following. So one condition that may seem strange and unmotivated right now is the fact that we want our solution, if you evaluate it at the origin, we want it to be finite. Okay. And so you may be thinking, well, of course it's going to be finite, right? It's temperature distribution. How would temperature blow up? Which, yes. And so kind of maybe the justification is, right, if we want a physically meaningful solution, then sure, we'd expect that it's finite everywhere. In particular, it's finite at the origin. Okay. But there's some kind of specific mathematical reasons that we're going to impose this condition that we'll see here shortly. Okay. So this boundary information right here, right, is telling something about what's happening right here. It's not really giving us a function value. It's just saying, well, whatever the value is, it's going to be finite. These two boundary conditions, right, these are related to what we saw with the circular ring problem. Okay. And so what these boundary conditions are telling us is that, well, what's happening down here, right, the value of our solution down here should be continuous and smooth, right, if we go here and then come out there. Okay. So these are essentially just saying that, sure, in this rectangle, it looks like this and this are different edges, but in practice, we want to treat them as the same edge. Okay. So anyway, so okay, with all that said, right, so this is the problem that we want to solve next. This is our PDE. These are all of our boundary conditions. Okay, and so we're going to apply the same strategy, right? Separation of variables, use superposition to construct a solution, and then we'll see what kinds of solutions pop out. Okay, so separation of variables, right? We want a solution that looks like this, where we've split up the phi or the theta and the r components. So if we plug this into the PDE, we're going to get an expression like this. Okay. So let's see, move this over there, divide by g, divide by phi. I guess this r squared gets moved over there. Okay, so move things, or plug in, move things around, we're going to end up with this expression. Okay. In particular, we're keeping a minus sign with phi. And so then, right, well, this only depends on r because g is a function of r. This only depends on theta because phi is a function of theta. Each side is constant with respect to the other side. And so both sides must be equal to the same constant, which we're going to call lambda. Okay, so we're giving it the same name. Keep in mind, though, here, right, we're writing lambda with the positive sign because we have this minus sign that showed up with the phi pieces. Okay, so now let's write out what the ODEs are. Let's also figure out what the boundary conditions look like. And go from there. Right, so 2 ODEs we're left with, right? This is one of them, where this finiteness condition we're going to put onto the g function. Otherwise, the other ODE is this, where, right, we're asking, so second derivative of phi is minus lambda phi, where the boundary information is this. Okay, so the only piece of information, boundary information we haven't used, right, is u of r, or a comma theta is equal to, I think we call it f of theta, right? This will be used after we construct our solutions using kind of this principle of superposition. Right, but in particular, this stuff you can get by, right, going back here, plugging in phi and g. Essentially, as long as g of r is non-zero, you can divide through. All's good to go. Okay, cool. Great. So one observation is, well, we've actually seen this and solved this one before. Okay, we've solved this in the context of, right, heat equation for a thin kind of circular wire. Okay. Right, so we solved this before. What do the solutions look like? Well, phi is going to be a linear combination of sine and cosine. We're now lambda, right? Lambda could possibly be 0. But in general, this was the expression, right, where right, so this solution from this problem, where here was x equals 0, this was x equals L, this was x equals minus L. Okay. So in this case, right, kind of, again, we've solved this. Here's what the solutions look like. Plug in L, in this case is pi, right, because theta is going from 0 to pi or 0 to negative pi. So plug in pi for L. Okay, we get some cancellation. So root lambda is just going to be n. And this is for n possibly 0, but otherwise n positive. So our solutions look like this. Okay, phi of theta is equal to some constant times sine of n theta plus some constant times cosine of n theta. And of course, when n is equal to 0, phi of theta is just going to be a constant. Okay. Okay, so now let's, right, take what this eigenvalue was, plug it into kind of the other ODE, right, in terms of G, and then see what we get. So this was the ODE for G, plug in for lambda equals n squared, you get this. Okay, and now what we're going to do is distribute this derivative, right? So this is going to be r dr. So this applied to that times a second, dg dr, plus r times, right, this applied to the second. So r squared, d squared g dr squared. And then bring that n squared g to the other side. All that's equal to 0. Derivative of r with respect to r is 1. And so then we end up with this. Okay. And so now, right, the annoying thing is that this is not a constant coefficient ODE, right? Because the coefficients depend on, right, the argument of what we're trying to search for. But in this case, it's actually not too much of an issue, right? Which we'll see here in a second. Okay. So the strategy that we're going to use now is we're going to say, well, okay, sure, we could use some fancier techniques to solve this, right, or a non-constant coefficient ODE. But what we're going to notice is that, well, whenever we lose two derivatives in G, right, we're multiplying by two pieces of R. Whenever we lose one derivative in G, or take one derivative in G, we multiply by one thing of R, right? And then finally, right, when we take no derivatives of G, we multiply by no powers of R. Okay? So, right, the derivatives that we're applying to G, maybe we can find a way so that, right, whenever we apply a derivative, we correct for it by multiplying by R. Okay, so which functions behave like when we take a derivative that corresponds to, right, taking the power down from R? Well, those functions are precisely, right, they look like R to the P. Okay, or you could say, well, let's make a guess of G of R is equal to R to the P, and let's figure out what P is. Okay, so but let's actually see what that looks like, right? So this was the original ODE. Plug in R to the P for G. We're going to get, right, so two derivatives of this. P comes down, you have R or P times R to the P minus 1. Take another derivative, that P minus 1 is going to come down. So you're going to be left with, right, P times P minus 1 times R to the P minus 2 is exactly that. And then, of course, we're multiplying by an R squared. Likewise, P times R to the P minus 1 is dg dr, and then you multiply by an R. And then finally, this, not much you can do. Okay. But the observation then is, well, here we have an R squared times an R to the P minus 2. These multiplied together, we're going to end up with a R to the P. Likewise, R times R to the P minus 1 is going to give us an R to the P. R to the P is just R to the P. Okay, so each of these three terms has an R to the P that we're going to pull out right there. Otherwise, we're left with P times P minus 1 plus P minus n squared, and that's what we have there. Okay. Okay, and so then here, right, well, either R to the P is equal to 0, or this is equal to 0. Okay. Well, if R to the P is equal to 0, R must be 0, but we want this to be a non-trivial function. Well, right, so this only holds when R is equal to 0, but we want it to hold when R is non-zero. So what we're going to do is essentially get out that, well, this has to be 0. Cool. So what we've done is we said, well, we want a solution that looks like this. What must P satisfy so that the solution G actually works for this ODE? And what we've done is we've gotten it to a point where, well, what must P be? P must satisfy this equation. Okay. So now the question is, what P's satisfy this equation? So what we're going to do, so we can write it out. So distribute this p over here, right? You get p squared minus p plus p minus n squared plus p minus n squared is equal to 0, which gives us p squared minus n squared is 0. Okay. And so that's exactly kind of what's written here. So what must p be? Well, p is going to be plus or minus n. Okay. So, right, for this to work, since we have a linear homogeneous ODE, right, we can use superposition to sum up solutions. So since we've seen that, right, we have two choices for p, we're going to have these two options right here. So our function, g of r, is going to be this linear combination. Okay. Okay, so now let's see what these coefficients might be. So g of r, right, is defined on 0 less than or equal to r less than or equal to a. Okay, so as r goes to a, or if you plug in r is equal to a, question is what happens to kind of this function g of r? Well, it's going to go to this linear combination. Okay, c1 and c2 are unknown constants. A to the n and a to the minus n, they're fine because, right, a is positive. Okay, positive radius. So, right, what's happening at a doesn't give us any information. But, right, we have other boundary information, right? We said something about what is happening with g at r equals 0. So if we say, okay, well, what happens as r goes to 0, right? What happens to this expression? Well, r to the minus n, right, as r goes to 0, this thing is going to go to infinity, right? This term is going to blow up. So if C2 is non-zero, right, then as r goes to 0, this thing is going to go to, right, infinity. So this is true if C2 is non-zero. And of course, right, for this other one, as r goes to 0, r to the n goes to 0, so this doesn't really tell us anything. But this term does tell us something. So our boundary condition, right, we wanted our solution to be finite at the origin. And so that translated to, well, the value of the spatial piece at 0 needs to be finite. Okay, so if C2 is non-zero, then this isn't satisfied, right? This condition is not satisfied if C2 is non-zero. So if we want this condition to be satisfied, we need C2 to be 0. Okay, so that's going to be our conclusion here. C2 has to be 0 because of this boundary condition. Okay. Okay, so that was for n non-zero. What about n equal to 0? Right. Maybe slightly easier. Right, for n equals 0, this is the ODE that we're going to get. Okay. Divide by r, right, that's just a 0 there. So then this will become, right, ddr of r dg dr is 0. Okay, integrate both sides. You're going to get a constant over here. This is going to be left over, which is exactly what's written here. Divide by the r, you're going to get this. Integrate once more, right? Integral of 1 over r is log of r. You have that constant in front. Otherwise, you're going to have this arbitrary constant, and that's what the C2 is. Okay, so this is the general solution when n is equal to 0, right? That other eigenvalue that we had. Okay, but again, we can argue the same way, right? Well, boundary condition says, right, plug in r equals 0. You want your solution to be finite. Log of r as r goes to 0, right? So log of r looks something like that, right? So log of r goes to minus infinity as r goes to 0. So if we want this condition to be satisfied, right, we can't have a log of r in our solution. So the coefficient for log of r has to be 0. So we conclude that, right, that coefficient is 0. And so when n is equal to 0, the resulting solution is just going to be a constant. Okay. So in summary, right, well, what do we get from all this? Well, so we know what the phi sub n are, right? These we solved before, that heat conduction in a thin circular ring. So these we got almost immediately. For the corresponding eigenvalue, which was n squared, we said, okay, well, what about the other ODE? We said, well, the other ODE has solutions that look like this. And this is for n positive. The other case we had to deal with was when n was equal to 0, right, for the 0 eigenvalue. So in that case, our spatial or our theta piece, right, well, even here, right, plug in n equals 0. That's going to go to 0. That's 1. So you're just left with a constant. And then the computation from the previous slide said that, well, g sub 0 is also going to be a constant. Okay. So now when we apply this principle of superposition, right, we're just summing up, right, all of these product solutions from n equals 0 up to infinity. And so, right, multiplying them out, distributing everything, what do we get? Well, phi of 0 times g of 0, that was just a constant. So that's just a 0. Otherwise, and so we can write it out here. So, right, phi sub n of theta times gn of r. This is c1 sine of n theta plus c2 cosine of n theta. All of that times some constant, maybe I'll call it c3 of r to the n. And if you distribute everything, you're going to get c1 c3 r to the n sine of n theta plus c2 c3 r to the n cosine of n theta. Right. So these are what these product solutions look like for positive n. Right. C1, C3 is just some arbitrary constant that we'll fix using kind of the other boundary information. So we're just going to call that some constant b sub n. Right? And otherwise, we have a C2, C3, that cosine term, that we're just going to call a sub n. Okay? But the takeaway is, right, this is our general, this is a form of our solution for kind of this, for Laplace's equation on a circular disk, which corresponds to, right, an equilibrium temperature, usually. Okay. Right, so then the question is, okay, well, right, we have information, we have, right, the value of our temperature at radius a. It's going to be this function f of theta. So, right, for the form of our solution, what needs to happen so that this is satisfied? Well, in this case, and so there's a typo here, right? So zoom in a little bit. Keep in mind here, we're plugging in, right, r is equal to a right there. Okay. So here we're plugging in, and here we're going to plug in. These should be a to the n, a to the n. Okay. So, right, for our solution to satisfy the initial condition, this expression needs to hold. But what we can do is use the same exact technique that we used before, right, where we multiply by, say, sine of n theta, integrate from, right, negative pi to pi. These terms are going to go away. These terms are going to go away. And so then we're left with, right, for example, we'll get integral from negative pi to pi, f of theta sine of n theta d theta, right? Multiplying left-hand side by sine of n theta and then integrating. Multiply the right-hand side by sine of n theta and integrating. This is going to go away. All of these terms are going to go away. And I can write it as a sum. This is going to be a sum from n equals 1 up to infinity of our unknown constant b sub n times a to the n times the integral from minus pi to pi of sine of n theta sine of m theta. I guess that should be m, but whatever. D theta. Okay. The only piece that survives here is when n is equal to m. And so then we're going to be left with b sub n times a to the n times this integral, which is going to be pi, is equal to this thing right here. And that's exactly what we have down here. Okay. So it's the same exact technique that we used in figuring out what these coefficients are for the thin circular ring. It's just now we have this extra piece a to the n tacked on, but that's fine. We can just divide through, all as well. Right, so that's isolating the sine coefficients to get the cosine coefficients, right? Same strategy, you're going to get these. Okay. Great, so we've solved it. Okay. And again, right, so this is our general solution for Laplace's equation in a circular disk, or the equilibrium temperature distribution in a circular disk. And the question is, well, right, for this solution, what are these coefficients? Well, we have explicit formulas for them. Okay, so we consider this problem solved. Cool. Okay. Cool. So the last thing that we'll talk about are the more qualitative properties of solutions to Laplace's equation. So they're going to be slightly less computational and kind of slightly less, yeah, we'll just leave it at that. Slightly less computational, but still they give some nice insight into what's happening. Okay, so right, from kind of what we just did, right, for the circular disk problem, okay, if we plug in r equal to 0, right, well, this was our general solution, okay, plug in r equals 0, we're going to get r equals 0 there. So these terms are all going to go to 0. The only thing that survives is a sub 0. And so a sub 0, right, it's going to be, well, this thing right here. This is just coming from, right, this formula right here. Okay. And so then, right, so here we're, well, what is f of theta? F of theta is the value of u at, say, radius a. Okay. Okay, well, so let's look at what this is telling us, though. Right, the value of the temperature at the origin, or at the center of the circle, is the average, right? So this is the average of the temperature distribution kind of on the edge of the circle. Okay. And so this turns out to be true in general. If you have a solution to Laplace's equation, it'll satisfy the sort of mean value property where if you take a circle around kind of the point that you care about, and then take the average temperature of that circle, that average temperature is exactly going to be the temperature at the origin. Right, so in general, at least in 2 dimensions, okay, if we have some function like that, we're using Euclidean coordinates, so that this thing takes the form d squared u dx squared plus d squared u dy squared. Okay, if we have a function u that satisfies this, then the question is, well, what is the value of u at a point x comma y? what is true is that this value is going to be the average of the value of the temperature on the circle around that point. So maybe as written, I should have here an R0, right, where this circle is tight enough around that point. And so really this condition just comes into play to say, well, the circle that you consider, you don't want it to be outside kind of the region that you're interested in. The circle, right, make sure that your radius is small enough so that that circle is in this region. Maybe I can draw a picture, right? So maybe this is our region R. And we have some function u that satisfies this in the region. And so what this is saying is that, right, the value of u, right, at a point is going to be the average of the value of u on the circle. And so you don't want the circle to be outside of the region. And so that's why, yeah, I don't know, it should be small enough. Okay, but so this, though, right, this statement that holds true for these kinds of functions, which we won't prove, but whatever. This is kind of the mean value theorem for solutions to Laplace's equation, right? Where the temperature at a point is the average temperature along any circle centered at that point. Okay. Which, may be interesting in its own right, but what we're really going to do is use this to establish kind of another result that's going to be a little more, I don't know, valuable for building intuition for these things. Okay, and so these other results are these things called maximum principles. Okay, and so what are these maximum principles? Well, right, this mean value theorem we just saw, one of its consequences is that if you want to know where the maximum or minimum of a solution u to Laplace's equation is, then that max or min must occur on the boundary of your region, right? And so in particular, going back to this problem, right? So, right, we said, well, the value of u right here is the average of the values of u right here. And so the question might be, well, maybe take this point. Can this point be the maximum of the temperature distribution? And the claim I'm making is that no, this cannot be the maximum. Okay. You could ask, well, what about like over here? Could this point be a maximum? And I would say, no, it cannot be, because all the maximums of the temperature distribution have to be on the boundary. And so this is what we're calling the maximum principle. Maximum of your solution to this has to be on the boundary. Likewise, the minimum to your solution to this has to be on the boundary. Okay, and so kind of how does that go? Well, suppose not. Suppose the maximum occurs somewhere in the interior. Okay. So what we can do is we could say, well, the mean value theorem says that the value of the temperature, right, kind of is in the interior, or sorry, the value of the temperature is the average of the temperature on this circle, right, surrounding it. Okay. But if u is a maximum, okay, then it doesn't matter what these values are, right? Because here we're evaluating u at different points. Whatever these values are, these values are all going to be less than this, because we're saying, well, u is a maximum temperature. So all of these values are less than this. So this whole integral is going to be less than this integral, where all we have changed is replacing these values by the larger value u of x. But of course, right, well, here, this doesn't depend on theta. So this you can pull out. The integral from minus pi to pi of, or d theta, that's going to be 2 pi. So this integral is just going to be equal to this. Okay. So what we've done is we said, well, if u is a maximum, then u, the value of u at xy, is strictly less than the value of u at xy. Okay. And so it tells us that, well, right, maybe your assumption that u was a maximum, or u had a maximum at x, y, that assumption is false. Okay. And so this holds true for any point in the interior, right? Take any point in the interior, you can find a small enough circle that encapsulates it, okay? And then the mean value holds there, okay? So wherever this holds, or wherever the mean value holds, we can use this argument to say that, well, u cannot be a maximum there. Okay, so where are the points where the mean value doesn't hold, right? Where are the points where you can't draw a small circle? Well, if you take a point on the boundary, as soon as you try to draw a small circle around it, right? So in here is fine, but out here, you're going to be leaving the region R. So for points on the boundary, you cannot draw the small circle. So for points on this boundary, this mean value theorem doesn't hold. And so points on the boundary, right, this doesn't come into play. So, right, where are we possibly going to find a maximum? Maximum are going to be found on the boundary, at least for solutions to this. And you can use the same strategy to show that the minimum value of u must also occur on the boundary, right? And so, right, how would that work? Well, assume that u has a minimum. This value right here is going to be larger than the value at the minimum. And so then all you're doing is changing this, the direction of this, but you get essentially the same contradiction. Cool. So, right, solutions to Laplace's equation, the maximum minimum have to occur on the boundary. Which already, so if we go all the way back, where's the picture I drew? So yeah, so as an application, if we go all the way back here, right, and you ask, okay, for this solution u, what are the possible maximum and minimum? Well, the maximum and minimum for this solution u, from what we just said, by this maximum principle, the max and min must be found on the boundary. So we say, well, okay, what does this boundary information tell us? Maybe the max is right there, maybe the min is right there. And all the values for u in the interior have to be between this maximum and that minimum. Likewise, if we go all the way back here, right, to Laplace's equation on a rectangle, okay, maybe let's go here. Right, same reasoning. Max and min must occur on the boundary. So we say, okay, well, for our boundary information, where are the max and min? Maybe this is the max, maybe this is the min. And so whatever the solution u is in the interior, the values in here have to be between this value and that value. Yeah, which is pretty neat. Right, so without actually like going in and finding the max and min of these series solutions, right, we can already say something worthwhile about these solutions. But, okay, cool. Okay, and so then the last kind of piece that we'll look at in this qualitative realm is the stuff called well-posedness and uniqueness. Okay. So what is well-posedness? Well, consider, right, Laplace's equation in some region R. Okay. And suppose we're given boundary information, right, the value of u on the boundary. Okay. And so one question is, right, well, if you change the boundary condition by a little bit, is that going to change the solution U by a little bit or a lot? So what does that look like as a picture? Well, so here's our region R. And so maybe here's our solution boundary data F. So this is F. And so the question is, if we change this boundary information by a little bit, so what would that look like? Well, we consider something like this. So this is going to be G. So if the boundary information F and G are close, right? Because looking at this picture, sure, here they differ by a bit, here they differ by a bit, but like overall, they're fairly close together. If we solve Laplace's equation with respect to F, we'll get a solution. And if we solve Laplace's equation with respect to G, we'll get a solution. Question is, are those resulting solutions wildly different? Okay. And we'd like to say, especially from physical context, well, no, they shouldn't be too different because the boundary information doesn't change by a lot. And so our question now is, well, can we quantify that? And so it turns out by using the maximum principle, we can. Okay, so let's see how that plays out. Okay, so we have, these two problems. First one is U solves Laplace's equation in the region R, where on the boundary, U is equal to this given function F. Okay. And actually, let me copy this picture. Yep. Okay. So U, this U here, that's going to correspond to, taking this boundary condition F and then solving Laplace's equation. This function V right here is going to correspond to taking this function G and then solving Laplace's equation. Okay. And so what we're going to assume is that this difference, if you look at the absolute value of the difference, this quantity is always small, meaning that F and G, for any points on the boundary, the difference between F and G is always small. Cool. So, okay, so what does that give us? Well, so let's consider this new function W, which is going to be the difference between U and V. U and V both solve Laplace's equation, okay, but by linearity, W now also solves Laplace's equation because that, distribute this across the difference, you're going to get that. Each of these are 0, so you're going to get that. Okay. But now, well, what is the value of W on the boundary? Plug in any boundary point, U is going to be equal to F, V is going to be equal to G. And so W is going to be this difference on the boundary, F minus G. Okay, but here we can use the maximum principle. Okay, and so, well, let's use the maximum principle on W. It says that the maximum and minimum of W occur on the boundary. Okay, so the minimum of W, occurs on the boundary. What is W equal to on the boundary? Well, it's equal to this. Okay, so the smallest, the minimum of W is going to be the minimum of W on the boundary. So the minimum of W is going to be the minimum of this difference between F and G. Okay. Likewise, the maximum of W, the maximum is going to occur on the boundary. Okay, what is W on the boundary? Well, W is equal to F minus G on the boundary. So the maximum of W is going to be, so W is going to be bounded above by the maximum of this term, F minus G, right? Again, which is the value of W on the boundary. Okay. Cool. And so here, right, well, sure, if F and G are close, meaning that their kind of point-wise difference is small, then the minimum of this difference, right, which is small, is going to be approximately the maximum of this difference, right, which again is small. And so these are all going to be approximately 0, right? Again, if F and G are close, meaning that their point-wise difference is small. Okay. So what that tells us then is that, right, well, if this is close to 0, because F and G are close, and then this is close to 0, because F and G are close, then whatever F or whatever W is, it's bounded below by something close to 0, and it's bounded above by something close to 0. So W itself should be approximately 0. Okay. Right, but W was a difference, right? Right here. So W, this is the difference U minus V. So this difference is approximately 0. So U is approximately 0, or U is approximately V. Okay. And so this is how we've quantified, well, if, right, these two pieces of boundary information are close, then the corresponding solutions U and V must also be close. Okay. Cool. And so, right, essentially the same argument works to say, well, right, can you have two different solutions to the same boundary condition? Right. So maybe F is equal to G. And so then the question is, if you can find a U and a V such that U and V are different functions. Right. And the answer is no, because, right, same reasoning. If F and G are the same, then this quantity is going to be 0. This quantity is going to be 0. So W is going to be exactly 0. And so then in this case, U is going to be exactly V. Okay. And so this gives us a sort of uniqueness condition for solutions to Laplace's equation, right? Given Laplace's equation, given some boundary information, there is a unique solution to that problem. Okay. This doesn't tell you anything about actually finding that solution or if it exists, but if such a solution exists, it must be unique. Okay. And so our computational examples have been showing, well, they exist. We can actually construct them in some way. And so then this gives us that uniqueness. Cool. Okay. And so then the very last kind of related point, I guess, is going to be this thing called solvability condition. Okay. And so essentially what this comes out to is kind of using the divergence theorem to translate kind of what's happening on the interior to what's happening on the boundary, and then reasoning about that. Okay. Right. And so in all of these examples, right, we've said, hey, well, here's boundary temperature, say, here's a condition on the boundary temperature. What does the solution look like? And in general, we've been able to come up with these solutions and say, yes, we can actually have such a solution. Right. But if instead of prescribing temperature on the boundary or kind of function values on the boundary, if instead we specify flux, or kind of equivalently, if we specify what the derivative of the function should be, okay, then it's possible we may not actually get solutions. Okay. And so here's a relatively quick trick to figure out whether kind of the information you have about the flux is enough to get solutions. Okay. And so, right, so recall Laplace's equation, we're solving Nablus squared u is equal to 0. Okay. So what we can do is, right, well, what is Nablus squared equal? What is Nablus squared? That's the divergence of the gradient. So we say, okay, well, right, what is this integral over the region R? Well, if you integrate Nablus squared u is equal to 0. So this integral is 0. Okay. But we can write this in divergence, right, as div grad. Here we can use the divergence theorem. So this is integrating over the region. This is integrating over the boundary, where the divergence theorem says, right, integral of divergence of a vector field A over the region. This is the integral over the boundary of A dotted with the normal vector, and then integrate over the boundary. Okay, so this step is divergence theorem, but what we get here is that, right, the integral of the gradient of the temperature, which is related to the flux, the integral of this gradient over the entire boundary must be 0. Okay, so this is something that we're calling the solvability condition. Okay, another way to interpret this is to say, well, if you want an equilibrium temperature, okay, and you don't have a source term, well, whatever energy is flowing in, right, that amount of energy must be flowing out. Okay? And so intuitively that makes sense. So the question is, well, how do we quantify it? This is exactly the way we quantify it, right? The flow of temperature over the boundary integrated over the entire boundary must be 0. Okay, so you can have stuff flowing in one portion of the boundary, okay, but whatever you have flowing in must also be flowing out if you'd expect to have an equilibrium solution. Yeah, okay. And that's it for qualitative properties, and that's it for chapter 2 of Haberman.